There is a fierce competition taking place every year that pits teams of robots against each other to compete for glory. This competition is known as RoboCup. Consistently drawing over 350 teams and 3,500 participants per year, RoboCup is an intense experience for anyone that partakes of the action. It's predicted that by the middle of the 21st century, a team of soccer robots will beat the current FIFA World Champions. This goal has just gotten closer to reality with the design and production of the soccer robot affectionately known as Charles, brought to you by QUT's EGB320 Team 12. The prototyping and evaluation of Charles took place in a controlled environment, namely a 2x2 meter field with 2 goals on opposing sides. The field surface was a green felt, while the goals were painted blue and yellow, respectively, for identification purposes. Charles was designed according to a large set of given specifications. Some general specifications include the maximum size of the robot being a cylinder of 180 millimeters diameter and 225 millimeters height, the robot not being allowed to cover more than 20% of the ball's cross-sectional area when viewed from above, and the robot must be mostly black. Each subsystem also had a set of criteria that it was required to reach. Chris's drive system must be able to consistently reach or exceed a translational velocity of 0.5 meters per second. My kicker system must be able to kick the ball at 2.5 meters per second or over. My dribbler system must be able to retain the ball when moving from one side of the field to the other at a velocity of 0.5 meters per second. Kane's vision system must be able to consistently identify the ball, obstacles, the walls, and both goals, as well as providing accurate ranges and bearings. Finally, Scott's AI system must be able to score goals and avoid obstacles given an unseen starting position. In all cases, the subsystems must be contained within well-designed covers.
The drive system designed for and implemented on Charles is a 3-wheeled omnidirectional drive system powered by stepper motors. It is an open-loop control system. The stepper motors are each controlled by a stepper driver, which are all controlled by a teensy. The AI system provides a distance, heading, and velocity. The drive system, which then computes maths for each wheel on a separate core of the Raspberry Pi, and then hands down these instructions to the teensy via a USB connection. All of this results in a highly reliable, accurate, and quick drive system with a full range of motion.
The dribbler system was initially implemented using a design based off the Robo-Roost soccer robot, but was later changed to a simple barrel with an indent in the middle to keep the ball centered due to the ridges knocking the ball away. Additionally, rubber bands were attached to the dribbler to increase friction when contacting the ball, increasing the effectiveness of the dribbler. For the kicker design, many different options were considered, including solenoids, spring and DC motor mechanisms, and pneumatic systems. It was decided that a spring and DC motor mechanism would be the best, as they are simple, infinitely repeatable as long as you have charge, and they have a fairly strong kick. I chose to use a rack and pinion gear set in tandem with the DC motor and springs to create my kicker system. This design was largely influenced by the restricted space available.
The vision subsection is able to segment the ball, obstacles, wall, and the goals and return their respective bearing and distances accurately. The process implemented is converting a PiCam RGB image to HSV color space so that the image is less affected by change in light. After which, thresholding takes place, which removes any pixel not within the bounds of the hue, saturation, and value predefined. This constructs a binary or mask image, which is then eroded and dilated to remove false positives. Fine Contours finds the shapes that remain, and based upon the size determines what type of object it is. The object's X and Y is used as the position and the length, width or radius used to determine the object's distance and bearing alongside a previously calculated focal length and pixels per millimeter. These values are then returned to the AI subsection. Alternative color space methods were considered, in particular the RGB color space. However, HSV was selected because it was less affected by light variance.
The AI navigation used the potential field method because the robot had to be reactive to an environment. This meant that it was attracted to the ball and repelled by all obstacles. I designed the state machine to initialize all systems, then to search for the ball, get to the ball using the navigation, and avoid obstacles, and then push it into the goal. Furthermore, the navigation, drive system, and vision had to be running at the same time, so threading had to be implemented to make sure that they're running smoothly and effectively. Alternative methods for the navigation were considered, such as making a map, using planning such as A-star, get to the ball, avoid the obstacles, and push the ball into the goal.